In section 3.1, we've been learning how to graph exponentials. We've defined what it meant to be an exponential function, and now we're going to go a little bit deeper into what that letter E represents. If you remember from the beginning of section 3.1, we learned how to use these exponentials and use our calculator. How do we plug in basically just an exponent in general if we had an exponential function? And the second one we looked at was we had a base of E, and we saw that there is an E to the X button on our calculator. And I mentioned that the E is not a variable, and that we would go into this a little bit deeper in a later video, later part of this section. And here's where we're going to talk about what that E means. It's almost like a variable like pi. We know that we're taught that pi is equal to 3.14. Well, the E is what we call the natural base. And you need to know that it's called the natural base. You need to know the name of E. It is an irrational number, just like pi, and we approximate that at 2.72. And again, you need to know that it's called the natural base. When you see that E, it's called a natural base, and this is what it's actually more equivalent to. Just like we know pi is not just 3.14, E is not just 2.72, but we just use that to approximate what E is equivalent to if we're going to use it in a function. But my suggestion would be always use the E button in your calculator and not just the 2.72, because you're going to actually, if you're approximating a decimal, you're actually going to be off by a couple decimal points. Just a few numbers off, because you're just rounding it and not using, fully, for instance, the 2.718281827. The more places you round, the more accurate of an answer you're going to have. But it is about 2.72. When we see it in a function, if we don't just say, okay, well, here's E to the 2.3 power, that would be called, okay, there's the natural base. If we write this in function form, if we actually set it up as an equation, then it's still called the natural base, but now it's just called the natural exponential function. Okay, so just keep those words in the back of your mind and know that it's called the natural base, or it's called the natural exponential function. And you can kind of see this table 3.2 over here. This is just for your reference to kind of show how it in a way kind of came about with the 1 plus 1 over n to the nth power. As these numbers got increasingly big, and then you're plugging in, from 100 to 10,000, and the answers are not really changing. That just kind of shows the progression of how it came about. And one of the areas that you will see the natural base E being used is in compounding interest. Okay? Now, not going to read all this to you. This is all in your textbook, and of course you can print this out and kind of keep this handy. This is just for your reference to kind of go in a little bit more detail and a little bit of background into compound interest. And what we're actually trying to get to is when we talk about compounding interest, what we do want to pay attention to is there is a specific number of compoundings per year, depending on what you're investing and how you're investing it. Now, to kind of skip ahead just a little bit, this is our formula for compounding interest. And all of this is explained above. You need to know what these variables represent. Of course, your A is your amount. That's what we're trying to figure out. What is my amount going to be? The P in that formula is your principal. How much are you investing? The R, so the P here, is your principal. The principal amount that you are investing. The R is your interest rate. And the T, of course, is time. Time is always given in years. Okay, and again, this is all kind of up here in some of this explanation. And the N is the number of compoundings per year, and that's going to change based on the wording of the problem and of course what investment we're going with. Now, the number of compoundings, it can be semi-annually, it could be quarterly, it could be daily, it could be monthly. There's all different kinds of options on how you want your interest compounded. By that we mean, when is your interest going to be put into your account? Is it going to be twice a year? Is it going to show up in your account quarterly, so 4 times a year? Monthly, so at the end of every month? Most, for instance, if you have savings accounts, most banks or credit unions, at the end of every month, you'll get a couple pennies, depending on how much you have in there, $1, $2, something like that, some change at the end of every month. It's compounded every month based on how much money you have in the bank. At the end of every month, they put some money in there for you. And that's your interest being compounded. Okay? So you've got to pay attention to the wordings to know how to plug in for N. If it's semi-annually, we plug in 2. Quarterly is 4. Monthly would be 12. Daily would be 365. It's all based on per year. Okay? Time is always given in years as well. So this is the formula for compounding interest. Now, there is also something called continuous compounding, which means that it's not just going to be N equals 2 for semi-annually or N equals 4 for quarterly. It's going to be continuous. And you don't have to know the progression of this, but here's your formula for compounding interest. And based on the idea of continuous compounding, it's all the time, non-stop going to be compounded. We eventually take this formula over to P times e to the RT power, and this is where our e, our natural base, comes in. Again, you don't necessarily have to go too deep into why it becomes that or how it becomes that, but there's 2 separate formulas, and of course that is wrapped up for you here. Again, if you have a specific number of compoundings, monthly, daily, quarterly, semi-annually, then we use this formula. If we don't have a specific number of compoundings, but it's going to be compounded continuously, then we use this formula. So you can see your example. So you've only got these 2 formulas. You have to know which formula to plug into, and then from there we just follow our order of operations. In example 6, you can see how we can apply these 2 formulas. So actually putting this into pretty real-life application, we're going to go and invest $8,000. And we know that we're going to leave it there for 6 years. And I go to invest my money, and the person that's doing this, my loan officer, tells me that I have a choice. I can put it into this account, and it's going to be an interest rate of 7%, and they're going to compound that monthly. So every month they're going to add money into my account, 7%. The other option that I have is a slightly smaller interest rate of 6.85%, but it's going to be compounded continuously. So, and a lot of people think, well, okay, compounded monthly, that means once a month they're going to add money to my account. Well, if it's continuously, then they're continuously all the time adding money to my account. It doesn't necessarily work just exactly like that. But we want to know which one's going to give me the most amount of money at the end of 6 years. So I'm going to pick out and first label everything that I have. Of course, I'm going to be investing $8,000. That, of course, is my principal. Your principal is how much are you investing. And I'm going to be investing for 6 years, so that's my time. Remember, time is always given in years, so 6 years. And then I've got two separate parts. For part 1, or the first option that I have for investment, my rate, if it's 7%, we know that we cannot plug in percent. We have to change that or convert that into decimal form. So to drop the percent, we move that decimal 2 places to the left. So if you plug in 7, you're going to get an incorrect answer. And it's going to be compounded monthly. The number of compoundings is the N. And if it's monthly, we know there's 12 months in a year. So that's how I get my number of compoundings. Now, a lot of people say, okay, well, when I plug this into my formula, so this will be option 1. I'm going to plug into A equals P times 1 plus R over N to the NT power, and I know that I'm using that one because we use that one if we have a specific number of compoundings, and I do. They're going to give me compoundings monthly. So that's a specific number of times they're going to add my interest into my account. So I know that I'm going to have to use that formula. Now, a lot of people say, well, if I've got 12 compoundings per year, and I'm going to use that or do that for 6 years, then don't I have to convert that and say that, multiply that 12 and 6 and say, well, that's my number of compoundings? We don't do that. If you do that, you'll come out with an incorrect answer. You plug in what they give you, because look right here in the formula. That's where it's going to multiply the 12 and the 6, and the formula takes care of that for you. You don't have to make that conversion. Okay, you don't have to actually plug in or convert that to 72 for your number of compoundings or whatever the case may be. The formula does it for you. You plug in what they give you. If it's compounded monthly, that's 12. You will never change that. You won't say, well, if it's for 2 years, I'm going to plug in, 24. You don't do that. The formula does it for you. So let's plug in what we do have and see what happens if I choose this account. Now, my principal is $8,000. In parentheses, I have 1 plus my rate is not 7, but 0.07 over n, which is 12. And I'm going to raise that to the n times t power, which is 12 times 6. So that's where it computes that for you. You have to follow your order of operations, which means I've got to do everything inside this parentheses first and inside the parentheses also, to kind of show you how to apply this on your calculator. If you do 1 plus 0.07 over and then divide that by 12, you're probably going to get the wrong answer. You've got to, inside the parentheses, still follow the order of operations, which means I have to do the division first. So I've got 0.07, divide that by 12, and then we add 1 to that. It gives me 1.005833333. So just inside my parentheses, I got 1.0058, and then I had a 3 repeating. We're going to go ahead and raise that to the 72nd power because this is 8,000 times. So again, following order of operations, I've done what's inside my parentheses first. Now I have to do the exponent part first. So since you've already got that in your calculator, you're just going to raise that to the 72nd power, which gives me 1.520. Of course, the more decimal places you round that out to, the better off you're going to be, and the more accurate of an answer you're going to have. So this is still 8,000 times, and raising that up to that power gives me just approximately 1.520. Then we can multiply that by 8,000. So my final amount at the end of 6 years is going to be multiplied by the 8,000, and I get $12,160.84. That was $12,160.84. So, not going to get rich on $8,000 with a 7% interest rate. Okay, so we've gained a little bit. Well, let's see what would happen in scenario 2. For scenario 2, I've got 6.85% interest rate, so that's going to be 0.0685. So to drop the percent off, we have to move that decimal 2 places to the left. So there's the rate that I'm using on that one. The formula for this one is A equals principal times E to the RT power. Now, following the order of operations, we have to keep in mind that that P is times the E. The E is what has the RT power here. So again, we'll have to make sure that we're going to do exponents first. So when I plug in what I have, my principal is 8,000, same principal, times E. I'm going to raise that to the RT power. So 0.0685. We're still using 6 for time. The only thing that's changed is the interest rate and the formula that we're using. On this one, this is going to be 8,000 times E to the 0.4 411 power. And again, that would be, I would take my 0.0685 and multiply that by 6, and we get 0.411. That's a terminating decimal. So I didn't round that. That's exactly what I got. And I'm going to take the e and raise it to that power, which gives me, well, I just clicked off my calculator. But that's going to give me 8,000 times, let me pull that calculator back up so we can follow that. That's going to be my 0.411, raise that to the, or put that as the exponent to the e. Again, I have to work my calculator backwards and put in the exponent first and then put in the base of e. That's just the way my calculator works. And then multiply that by my principal of 8,000, and we should get a number pretty close to what we got in step 1 because there's not much difference between these two. And you can see that I do. I get 12,000. Let's see. 12,066.60 for my amount. And although we are going to have $12,000 at the end of the day, at the end of the 6 years, this one still gives me slightly more money, so I'm definitely going to go with the 7% compounded monthly. 7% compounded monthly is the option that I would go with if I was going to invest my $8,000, because it asked me which one is the better investment. The 7%. Even though, and one thing is, don't just always go with the one that has the higher interest rate. Depending on how it's compounded, then it will change your numbers. So you don't just automatically assume it's going to be the higher interest rate. It can come out that the smaller interest rate will give you the most amount of money depending on your compoundings. Okay, so that's just one application of how you can use the E. One thing, the most important thing you need to understand is you have to be able to work your calculator, because calculators can give us the wrong answers based on how we use them and how we type them in. So, and one thing on these is your answer should make sense. If I would have come out with an answer of $50,000, obviously I would be, a little skeptical of that answer, because you're not going to have $8,000, put it in the bank, and it's just going to turn into $50,000 over 6 years. It should be a relatively small amount that we're going to earn. And so your answers should always come out to be close, around the same amount, and they should come out to be reasonable numbers.